Hi, this is Dr. Simon Romero, and I'm here to present you the video tutorial for section 14.5, directional derivatives and gradient vectors. These are the topics that we're going to cover, and the practice problems. As always, I suggest you to do them all. Let me start with the geometric representation of the partial derivatives. This is actually something that is useful for understanding partial derivatives, and it's going to lead us to the reason why we need directional derivatives. So let me start. Let's start with the function, the graph of a function of two variables. And notice that here I am just highlighting a point A in the domain and a corresponding point in the graph. So suppose that I take just the line y equals to b, and I actually take the plane y equal to b in the three-dimensional space. That will intersect the graph of the function. And the question is, well, can I parameterize this graph of the function? And the answer is yes, and I can do it like that. This parameterization parameterize the curve using x as the parameter. Why x? Because x is the only variable that is moving. Why I'm doing this? Because if I take the derivative, will give me a formula for the tangent vector to a curve for every x. And notice that if I take the derivative and evaluate at the particular point, the thing that I obtain is that the partial derivative gives us the inclination of the tangent vector. So in other words, there will be the inclination of the tangent line with respect to the positive x-axis. For example, in this case, the partial derivative is negative because this vector in the z-axis is going down. We can do the same thing for y, so I will take the plane x equal to a, intersect with the with the graph of the function. I will obtain a curve that if I parameterize and I take the derivative, it will give me a tangent vector that I just drew over there. And if I just evaluate, I have 0, 1, the partial derivative of f with respect to y at that particular point, and again it gives you the inclination with respect to the positive y-axis. In this example, again, it will be negative because this vector, the z component of this vector, is negative. So here are both vectors together, and now let me tell you what's the idea of the directional derivative. So suppose that you have the graph of a function. If I move in the direction of I have this tangent vector that, again, the partial derivative will give us the instantaneous rate of change of the function when we move in the direction of I. The same thing, we do it for j. So the partial derivative will give you the inclination of the tangent line in the direction of j, or in other words, the instantaneous rate of change of f with respect to a movement in the direction of j. So suppose that we take another different unit vector. So the question is, can we find a way to compute the instantaneous rate of change in the direction of the unit vector u? Well, in other words, we want to know what is the z component of this vector right here. So let me tell you a little bit more about partial derivative. So remember that in the definition of partial derivative, the partial derivative of f with respect to x was this limit right here. And notice that we are adding h only to the x component. In other words, if we move from AB to h units from AB, the thing that we have in the direction of x, the thing that we get is this particular ratio, and then when you take h going to 0, gives you the partial derivative with respect to x. So notice that in here we're moving in the vector hi that consists of the components h, 0. Well, we can do the same. Now, in the y direction, now we're moving in the direction using the vector hj. We're moving h in the direction of j. And the thing that we have is we're adding h here and 0 in the x-axis. So when we are moving in hj, the direction of the vector hj, that happens to be 0, h. So the question is, well, now consider a unit vector u and move h units in the direction of u. So in this case, if u has components u1 and u2, you are moving in the direction of hu that has components hu1 and hu2. And the most natural thing to do is take the limit when you are adding HU to A, HU1 to A, and HU2 to B. And notice that that will give you the difference between the original point and the point after we move H in the direction of U. So that's going to be the definition of the directional derivative. This is going to be the limit definition, and it's not going to be very useful to help computing the directional derivative. So the question is how we're going to compute the directional derivative. Well, first of all, it's important to know that the vector has to be a unit vector, and the reason is because of what we have here, because we were moving H units in the direction of U, but U has to be a unit vector in order to have HU to be the vector that moves H units in the direction of U. So let me teach you another way to compute the directional derivative. Take the vector U, and I'm going to take the line containing the vector U. So first I'm going to parameterize this line. Since the thing that I'm going to concentrate is movement in the direction of U, and H was a good way to describe how much you move in the direction of U, let me parameterize it with respect to H. So the parameterization is pretty simple. You just take the starting point AB, and then you're going to move H units in the direction of U1 and U2. By now we should feel very comfortable of parameterizing lines. So now that we have these, the question reduces itself to say, well, what is the instantaneous rate of change of f with respect to the movement in this line? But the instantaneous rate of change of f with respect to the movement of this line is actually just the instantaneous rate of change of f with respect to h. So in other words, we have how much f changes with respect to h. Notice that this is just given by a chain rule. Why a chain rule? Because f depends on x and y depend on how much you move in the direction of u. So we use a chain rule. The change of f with respect to the change of x, and the change of x with respect to the change of a. And the same thing for y. And well, what we obtain is that, well, the change of in x with respect to the change of a is equal to u1, and the change of y with respect to h is going to be u2. So finally, the thing that we have is we have this formula by just plugging in what we have. Now this formula can be improved a little bit more by just saying, well, what about can I write this in a vectorial form? In other words, can I get a vectorial formula? And the answer is yes. Remember that every single chain rule can be expressed as the dot product of these two vectors, and that's the theorem that we have. So if you have that the directional derivative is going to exist if the partial derivatives exist, and they are going to be equal to the dot product of the vector consisting of the partial derivatives and the unit vector. Remember, this vector u has to be a unit vector. That's very important. The gradient vector. So the vector consisting of the partial derivatives is actually called the gradient vector, and of course that gives you immediately the formula for the directional derivative to be equal to the dot product of the gradient vector and a unit vector in the direction that you are trying to compute the directional derivative. So let me give you an example. Find the directional derivative of this function at the point 2, 0 in the direction of the vector that makes an angle of pi/3 with a positive x-axis. So the first thing is we compute the gradient, that is right here. Then we evaluate at the point 0, 2, and this is the gradient at the point 0, 2. Now the thing that we need to compute is the unit vector in the direction they are telling us. Well, first of all, if you recall from one of our earlier class activities, a unit vector in the plane can be characterized by cosine of theta and sine of theta. So in our case, the angle is pi/3, so you have that this is the unit vector. Now what do we do next? We take the dot product of the gradient vector that we obtained and the unit vector in the direction that they are giving us, and that gives you this particular number. What can we interpret from this particular number is that at the point 2, 0 in the direction of u, f is increasing at this rate. So let me just tell you the directional derivatives and the gradient vectors of functions of three variables. The idea is pretty much the same. You can extend it, the directional derivative, to functions of three variables by just adding the third variable, and the gradient vector is going to be the same, and actually the formula for the directional derivative is going to be the same. So this is, you can extend it pretty easily to higher dimensions. Now we're going to see how the directional derivative behaves with respect to the gradient vector, and for that we're going to talk about maximizing the directional derivative. So we know that the formula for the directional derivative is the dot product between the gradient and a unit vector. So since we know that the dot product can be also expressed as the magnitude of one of the vectors, in this case the gradient, times the magnitude of the unit vector times the cosine of the angle between the two vectors. Now in this case u is a unit vector, so its magnitude is 1. So we obtain this formula. So what can we tell about the directional derivative in this formula? First of all, the directional derivative, it's going to be the highest when the cosine is the highest. The cosine is the highest when it's equal to 1, and that happens when the angle is equal to 0. So one of the things that we can say is that the gradient vector points at the direction of maximum rate of increase. In other words, the vector gradient and u have to be parallel in order to have, or point at the same direction, in order to have a cosine equal to 1 or the angle equal to 0. So the highest that the directional derivative can be is going to be the magnitude of the gradient. At the same time, the lowest that it can be is when you are pointing in when the gradient and the unit vector are pointing in opposite directions. So in other words, the gradient minus the gradient vector points at the direction of maximum rate of decrease, and the minimum value of the directional derivative is going to be minus the magnitude of the gradient vector. Let me give you an example. Olga Olafsen is the world's toughest mountain climber. She always takes the steepest route mountainside. Suppose that she finds herself at this point in the surface of Mount Gauss. It's a fake mountain, and this is the elevation at the point xy. So in what direction she should head to maintain her reputation? So the idea is we just need to find the gradient vector at the point where she's at, and that will point in the direction of maximum increase. So this is the function that we're taking, and the thing that we need is to compute the gradient vector at the point 1, 3. So first we need to compute the gradient vector in general. The gradient vector in general is given by this. Now when we evaluate on 1, 3, it gives you a vector like that, or the thing that we have in the middle. So that will be a completely valid answer if you do this in a celebration of learning. Now if you want to help Olga in order to give her a more friendly vector, the only thing you can say is, well, look, since this is a positive constant, the vector minus 1, 2 has the same direction as the gradient vector as 1, 3. So she should just follow that direction. This last part is not necessary, so if you get to in a celebration of learning, as long as you get this or this vector, you will be fine. So let me just tell you about the gradient vector and level curves. So suppose that you have a level curve. Remember that a level curve are all the points that give you the same value under the function. So this is the level k of the function. So the level curve can be parameterized by a vector function. And when we plug in, instead of x and y, x of t and y of t, we obtain this equation right here. Now taking this equation and taking the derivative, in one side we're going to take is going to be the derivative of a constant, in the other side is going to give you the chain rule. But if you express this in a vector formula, we have that the gradient dot r prime is equal to 0 no matter what t is. In other words, we're saying that no matter what, the gradient of f is always going to be orthogonal to the level curves. So let me just put it here. The gradient vector is always going to be orthogonal to the level curves of f. Here is an example. Take that function. These are the level curves of that function, and then I'm going to graph the gradient vectors at particular points. And notice that these gradient vectors create kind of like a flow. This is called actually a vector flow. And with this, we finish the video tutorial for this section.